It's difficult for me to pronounce. I just call you Suri, or it's okay.
Surya. Okay.
So I'll let the other thing. I'll call you Surya.
Yeah.
Dr. Surya. Okay.
Yeah. Thank you.
Nice to,
let's start. So good evening. Good evening, everybody. Distinguished Professor Ching-Long, PhD from Taiwan, also respected lecturers, dear students, and all distinguished guests. So first of all, let us give thanks to God Almighty for His blessing and grace, which allow us to gather here today in good health for these special occasions. The guest lecture of Professor on behalf of the Faculty of Science and Mathematics and also the Master's program in Data Science, I am deeply honored to extend our warmest welcome to you, Professor at Satya Wacana Kristen University in Salatiga, Indonesia. Okay, our campus is often known as a miniature of Indonesia. So this is because the students here come from almost every province across the country. So our university now currently has around 40,000 students, and
40,000.
40,000
is quite a big
40,000,
right? 40,000 is it?
14,000.
14,000. 14,000.
Yes.
All right.
Up to 15, okay. And they are, we are big enough, and they are distributed into 15 faculties, 15 colleges. And among of these faculties, there are at least 3, especially relevant to your department, the Department of Computer Science and Engineering at Tatung University. So we have also here Faculty of Information Technology, the Faculty of Electrical Engineering, and also the Faculty of Science and Mathematics, particularly in the master degrees, master program in data science. So we invited also the students from this faculty, mainly from the master program in data science. So they are now here. So as seen in the slide, so recently on September 10th, 2025, I, together with the head of data science departments, Professor Hannah, I had the privilege to visiting Tatung University in Taiwan. Okay, during our visit, I was very deeply impressed by the creativity and innovation showcased in the field of electronics, mechanical engineering, mechatronic, mechatronic, and also art. I think you have very interesting art in Tatung. I was truly inspired in that time. Okay, and I hope to bring some of those ideas and spirit innovations to share and teach to our students here at Satya Wacana. So we are very excited now to begin our academic collaborations with Tatung University. And today, this time, the guest lecture by Professor marks the very, very first activity in this new partnership.
I hope we can build a strong connection between each other.
It is very meaningful starting point for the future cooperation. Especially in teaching, research, and knowledge exchange, of course. So, once again, we express our deepest gratitude to you, Professor for your generosity and also willingness to share our expertise to us. Your presence today not only enrich our academic environment, but also strengthens the friendship and academic bridge between Taiwan and Indonesia, especially in the dynamic field of data science and technology. So we warmly welcome you once again at our campus, the WIB campus, where the WIB meets. Thank you very much, and also thank you for Pak Bambang for being the moderator. So you can start now. Thank you very much.
Great.
Okay. Without any delay, let us welcome to Prof to begin his lecture.
Okay. So first of all, I'll share my slides to all of you. Is that good? This?
Yes, it's good.
Okay. Okay. Yeah. So now I'll start this lecture. First of all, yeah. Hi, everybody. Good evening. Thank you. I will thank you all of you to join this lecture. I'm Ching-Long from Tatung University Computer Science and Engineering Department. Our university is Taipei in Taiwan. Yeah, it's quite a small university, about 4,000 instead of 14,000 in Satya Wakana University. Yeah, okay. And thank you. It's a great pleasure, a great honor for me to be invited to join your academic lecture by Professor Dr. Hannah Pahusip. Okay, yeah, Hannah. Okay, Professor Dr. Hannah. Yeah. So now I was in this talk. The topic would be knowledge graph, and the subtitle is structuring world knowledge. Okay. The agenda of this lecture will be divided into 5 parts. The first part is the fundamental, which roughly, so I'll spend 25 minutes for the first part to introduce the fundamental of knowledge graph, the fundamental components, things like that, for 25 minutes. And the second one will be knowledge representation, the standard knowledge representation formalism. I'll spend 20 minutes for that, and then I'll dive in the technical part, which is how to construct knowledge graph and the knowledge graph construction pipeline. What it is, it will be 25 minutes. Then will be 5 minutes break. If it's okay, I'll continue to go to the next topic if you don't want to go for a break. Then the fourth part will be application and the use case. It's 20 minutes for this topic. Then the tools and challenge. Finally, will be the question and answering session, and the conclusion is only 5 minutes. But I hope this lecture is not so serious. Okay, not so serious. I hope this lecture will be a freestyle. So if anybody want to ask a question, just press things like with your hands. So let me see. Then you can ask question, and then I will answer your question directly instead of the final parts. When at the last section of question answering, people maybe or a few is not in well condition. Okay, yeah. And in this talk, it's more like a tutorial talk. And in this talk, the object is hopefully by the end of this tutorial, you will be able to first of all know the definition of a knowledge graph, and you can understand what is the core components, the building block of knowledge graph. Then the second part will be you can explain how knowledge graph differ from a traditional relational database. Yeah, I mean, if you are familiar with relational database like SQL database, then hopefully after this talk you'll know what's the difference between the knowledge graph. I mean, if knowledge graph is powerful representation, then what is the difference between that? So it will be for your motivation to use knowledge graph to do more powerful things. Then you can recognize the key standard for knowledge representation. This part will be RDF, RDFS, OWL. All of these standards are coming from W3C, World WIB Consortium. Then there will be the process of you will know the process, the general process of knowledge graph construction. Then finally, you know knowledge graph, what is the major real world application, and still some other open challenge for knowledge graph. Okay, that's be for the after this talk, you can learn this object. Okay, so we dive in the first part. That's the fundamentals of knowledge graph. So what is knowledge graph? Based on a simple definition like this, we'll say a knowledge graph, or just a brief abbreviation, say KG, is a model. It is used to represent the real world entities. I mean, entities like location or people like you and me, and some other concrete or abstract entities, and also the relationship between these entities. Knowledge graph is a model used to represent the real world entity and the relationship. If you are familiar with the database system, so when you want to build a table schema, you start from the problem description and you analyze the problem description to be an entity relationship model, ER model. An ER model is something like the entity and the relationship I'll talk here, but the knowledge graph is more semantic rich model for as a more semantic rich representation. I will show you later on. So the knowledge graph forming a network of interconnected information. All of these entities carry some information, and the relationship between entities. So it's will be a network of interconnected information, interconnected by a graph. So in knowledge graph, it's organized knowledge. It organizes knowledge by focusing on semantics rather than just its structure. Okay, so I'll dive in semantics, the meaning of the data, instead of the structure, just its structure. Okay, so then we go to the core components of knowledge graph. The knowledge graph consists of three main parts, which is nodes, edges, triples. And if we see from mathematics point of view, KG is actually labeled directed graph. It's a kind of graph. You know, a mathematical graph consists of two sets. One set is node, and the other set is edges. And edges connects node. And if an edge has direction, then it will say it's a directed graph. And also on above the edge, we give it some labeled. So that will be labeled directed graph from mathematical point. Or if you're not familiar with, you're not good at mathematics, it's okay. But that's very simple, three words to describe what a KG component KG is. So in this graph, there are three components. The first one is nodes. Entity is represented the entities. Just before we define a knowledge graph, it's used to represent the entities in the world. So the entity now is represented by word. It's used to represent the real world object, concept, or events. Okay, the object will be some concrete object like person, or some other conceptual object, or I would say abstract object like some events, the movie. The movie is actually like abstract idea, something. Okay, so for in this knowledge graph, the first components are nodes. Okay, so things like we represent graphically, it's an oval shape, it's nodes. Okay, then edges is used to connect a pair of nodes. So in this picture, the left-hand side is Eiffel Tower, and the other end of the entity is Paris, and between them is some directed edge, On the edge is a label located in. So you can understand this is consists of three components: entity, and relationship. There are three things that's here we said that's triples. Okay, that's triple. Triple is used to represent some sort of facts. So in this triple, it record the facts about Eiffel Tower as located in Paris. Eiffel Tower is the subject, located in is the predicate, Paris is the object. So we'll say triple is expressed as a subject, predicate, object, or SPO structure. Okay, so the core components of a knowledge graph is very simple. Three things: nodes, edges, triples. Okay, and so when we said what's the size of your knowledge graph, we used to say how many triples in your knowledge graph instead of how many bytes, how many gigabytes or something. We used them how many triples in your knowledge graph. So maybe your knowledge graph has some millions or billions. Billions is very, very big. Okay, millions is quite large one. Okay, so the core components here. A knowledge graph consists of these parts. Okay, and then the key characteristics of a knowledge graph. The key features. First one is semantic richness. For a knowledge graph, it captures the meaning of connection, not just a link. For example, when you are surfing the web, you use the hyperlink to connect your current page to another page. It's technically a hyperlink is a link to another page, and there's almost no meaning on the link. But in knowledge graph, the connection, the edge, the directed edge has bearing meaning for the connection. Okay, so it's semantic richness, and also the meaning is not for human to understand; it's for computer, for machine to understand, to process. Okay, then the second features would be the flexibility. It is for knowledge graph. It is very easy to accommodate new entities and relationship without needing a rigid predefined schema. Things like relational database, the table schema. The table schema is a predefined schema, and it is very rigid, and you can follow the table to fill in the data. But if you want to extend the table, it is impossible, almost impossible. But on the contrary, for knowledge graph, it's very easy to extend. So the flexibility will be for knowledge graph is very, as compared with relational database, is very good. And also the feature of inference and reasoning. Okay. The structure, the knowledge graph structure, the nature allows for the deduction of new facts. For example, I would say if a city is in a country and a person lives in that city, that city refers to this city. Okay, then the person lives in that country. It's a very simple reasoning, very simple inference based on the logic inference. Okay, but in relational database, there's no inference or reasoning capability inside the table. You can only use some query to based on the relational algebra to join two tables to get what you want. Okay. Okay. That here is the summary about to compare with the knowledge graph and the relational database. First row is the focus. Knowledge graph focus on relationship and semantics. Semantics is a very important thing here. But for relational database, it's table and data storage. It's only a table, a storage. So that's why it is so efficient, because relational algebra to make it so efficient. And then this from schema point of view, knowledge graph is very flexible and it can evolving. The ontology or the schema can change if you want, okay, if needed. But a relational database is fixed, is rigid, is predefined tables. It's not good for extension. And for data model, knowledge graph is a knowledge graph. The data model is graph, but relational database, the model is as a tabular structure. For querying, knowledge graph can use standard knowledge graph language, like for example Sparkle, to traverse the relationship, traverse the link within the knowledge graph. You know, when you traverse the knowledge graph, the path of traversal is something like a kind of inference. Okay, if we talk it based on the knowledge base structure. But for relational database, we can only use the join operation between tables to get what you want. Okay, for knowledge graph, it is best for complex, evolving, interconnected data. But for relational database, its structure is good for transactional data. Okay, then so here this slides show you some public knowledge graph examples. The first one is Google Knowledge Graph, but it's for internal use. It's the power of the information panels and direct answer in Google search. So when you search Google search engine, the background will be most from or something from the search engine's algorithm, but I think lots of parts is from Google's knowledge graph. Okay, but because of this internal, we can only use the API provided by Google to access the knowledge graph of Google, and also you have to put your credit card number there, because when you sometimes they want when you exceed some quantity, you'll be charged for some money. Okay, it's for commercial use. But the following three parts are public and open knowledge graph. One is Wikidata. You can use the Wikidata, or you just place this hyperlink I use here. You can access the Wikidata. And the other one is DBpedia. And for Wikidata, it's a collective, collaborative, multilingual knowledge base. It consists of millions triples. I think maybe more than million, maybe two. A couple of years ago, I accessed the Wikidata is about several millions of triples, but now I think it's enhanced to be maybe nearly thousands of millions, giga something. Okay, and the other public knowledge graph is from DBpedia. DBpedia, it's extract the structured data directly from the Wikipedia articles info box. You know, when you read the Wikipedia articles, there are some info box in the behind the Wikipedia article, and the DBpedia project, they extracts the structured data, that is the info box, directly to get the data and store in the knowledge graph. Okay, and Data Commons is an open source knowledge graph initiated by Google. It's focusing on integrating and normalizing vast quantity of public available statistical, socio-economic, and scientific data. Is quite a very valuable data. It's a valuable open knowledge graph. It's very good. Okay, so we have this public knowledge, but still there are lots of non-public knowledge graph on the web. Okay, you can access lots of, and there are many domain-specific knowledge graph on the web, okay, especially for life science and healthcare. Okay, but so now I will dive into another topic. yeah, here is the slides. I captured these slides from Cultural Institute of Technology, Professor Salah Halasak, for his lecture offered by him for knowledge graph. But his lecture is about 6 weeks every week. It's in lots of topics. So I won't use that slides. It's too big for this lecture. Okay, but it's good example from Professor Dr. Halasak's example. So here you can see a knowledge graph here, a solid graph, a black graph here. It's this triple. It says Leonard Nimoy played Spock, and Spock is a character in Star Trek. So it's there are facts about Star Trek movie. So the Star Trek, the genre is science fiction, and also another science fiction movies is Star Wars, and the most important character of Star Wars is Obi-Wan Kenobi. Obi-Wan Kenobi is a character in Star Wars, and who plays Obi-Wan Kenobi is Alec Guinness. Maybe you don't know who is Alec Guinness, but you know Obi-Wan Kenobi in the Star Wars. And also the blue parts, it says that it extends it's Obi-Wan Kenobi is a fictional character, and fictional character is a subclass of agent. And Alec Guinness is a person is a subclass of creature, and Star Wars is a film series. Okay, so if we say here this part is in a file about the Star Trek, and this part is about Star Wars, and both files can be loaded into memory, into computer memory, and they can combine naturally very easily, which means the knowledge graph can be extended very flexibly. So, and here we add some vocabulary to the notes in the left-hand side part. So it says Obi-Wan Kenobi is a fictional character. This belongs to this class, and fictional character is a subclass of agent class. Okay, and Alec Guinness is a person. A person is a subclass of creature, etc., etc. So you can see that the knowledge graph by Professor Dr. Halasak, it says the knowledge graph is mainly describe real world entities and their interaction organized in a graph. Here is a very good example. And then it defines possible classes, relations of entities in the schema. The right-hand side, this part can be seen as a kind of a schema about, okay. Then the third part is it allows for potential interrelating arbitrary entities with each other. And finally, it covers various topical domains. It's not restricted to some domain. You can very easy to extend it to other domains. So many different domains can be combined, can be mixed within a simple within a knowledge graph. And here is an example of the reference in the green parts. It says the problem is, can we solve? We can solve that via individual software code. This part can be coded into some program language, like like AI language, like AI program language, like Prolog. It's very easy to do that. But here we use this code. It says if Alec Guinness is a person and this triple person is a subclass of creature, then Alec Guinness is a creature. Both facts are true, then this triple exists. And we can conclude that this triple is also true. Okay, so based on this knowledge graph, we can do this part of the inference. And also we can do more inference. Said if Alex Guinness is a person, this triple says that Alex Guinness is a person, and person is subclass of creature. Things like the last slides. And Star Wars is a film series, and film series is different from creature. So we can conclude that Star Wars is different from Alec Guinness. Alec Guinness, the facts that Alec Guinness is a person, and the Star Wars, based on these facts, is a film series. But because of this triple is true, so we can conclude that Star Wars and Alec Guinness both are different from each other. Okay. Yeah. So this are more complicated, or more complex inference. But a question is, how do we, or how the computer know the meaning of the labels? This is a great question. Okay. So I will stop here for a couple minutes for you if you have any question.
Any question?
Or is okay?
Okay.
Yeah. So I'll continue. Okay. Yeah, I just stopped the projection of the slides. Down the here is the Professor Dr. Halasak. It's not his knowledge graph course offered by him in 2023. Okay, if you like, you can use Professor Dr. Halasak to get the course. It's free course. Yeah, you can if you want. They all have lecture notes, slides, and a video about the course. If you want to get some more deep idea about the lecture, you can go there. Okay, then I will continue. So our question is, how do we know the meaning of the labels? How do we know the meaning of labels? So one way is to use the formal representation to represent the knowledge. So for example, here, Obi-Wan Kenobi is a fictional character. Alec Guinness is a person, belongs to we use this symbol to represent a set. This entity belongs to this set, or this entity is an object in this class. Alec Guinness is a person, belongs to person set. Star Wars is a film series, and fictional character is a subset of agent. Here, fictional character is a class, agent is a class. For each class there is a set with the class. So the fictional character set is a subset of agent set. So, and the person set is a subset of creature, and film series and the creature, their intersection is an empty set. It says that they are disjoint to each other. And here is a logical inference. Alex belongs to Alex is a creature. Alec Guinness is not film series. Star Wars is not creature. So here is the new facts deduct from this knowledge graph. So it's if you know that the logic theory, the mathematical logic, you can know this is a formal way to represent the knowledge. It's the above facts. Here, the above the facts, and this is the new facts inference through the inference rules. Okay. Yeah, of course, you will say here is the mathematical representation. How can we represent it using some computer? How to make the computer know these labels? Yeah, of course, you can use program language like Prolog, P-R-O-L-O-G, Prolog, the program language, to encode the facts and the inference rule to do some inference. Yeah, Prolog is means programming in logic. but its logic is not first order logic. It's not whole set of first order logic. It's a subset of the first order logic. Just home close is a subset. But because if we use the first order logic as the programming language background, which will make it less, it's very complicated. So to make it more efficient, it's just the Prolog language just use the subset of the logic. Okay. Yeah, but we can say that here is a formal way to represent knowledge. This way is also comprehensible, understandable by the machine, by computer. But so far we have some standard for the knowledge representation. Okay. In last slide here is the logic representation, but here is we can see the semantic web. A semantic web is used to used to represent, is a formal knowledge representation. Okay, so it's quite different from traditional data. The formal knowledge representation is quite different from traditional data structures because it is based on mathematical logic, and the semantics of knowledge representation can be defined explicitly. Okay, it's defined explicitly instead of implicitly. So it's defined explicitly. So based on the semantics, the meaning of knowledge representation, we can do lots of inference to deduce, to conclude, to deduce the new facts. Okay, and mathematical logic enable inference reasoning for knowledge representation. I just said knowledge representation are defined explicitly. So mathematical logic can do logical reference based on the explicit knowledge representation. Okay, then we goes to the second part. I will talk about the semantic web standard for knowledge representation. We start from the challenge of knowledge representation. I will use KR as abbreviation for knowledge representation. So KG recap. KG is knowledge graph, but KR is knowledge representation. KG is a network of entities and relationships. The goal of knowledge representation is used to capture human like you and me, based on our understanding of the knowledge in this world, and the knowledge representation is used to capture the knowledge we understand into a machine readable, machine processable, and logically consistent formats. So that's the goal of knowledge representation. So but the problem, if we use traditional database, the table is not good with complex, interconnected, and involving relationships. We have talked in the first parts, said that's the problem of traditional database, relational database. So the solution is based on the triple. The solution, we use the triple to represent knowledge. The triple is what we talked about in the first part, the SPO, or the subject predicate object triple. It's the fundamental building blocks of a knowledge graph. The format SPO, subject predicate object, and the example, Paris is a city, Alice live in London, so things like that. Okay, so here's two examples of triples, and we use the triple to represent the knowledge we understand about this world, and to make it a format, a representation to be machine processable, machine understandable. So in the later on, the triple, I will make the triple to be machine understandable. Okay, some more examples will follow on. Yeah, semantic web standards hierarchy. It's a hierarchy of standards for semantic web. Semantic web is an initiative initiated from W3C. W3C is World Wide Web Consortium. Okay, the family of it's a semantic web standard hierarchy is a family of W3C standards that define how to represent knowledge on the web. Okay, the semantic web group is initiated from, I think, as far as I know, it was initiated starts from 2000, and all of the standards were formed by on 2004, and then in 2006 there is Link Open Object Data, Link LOD project initiated by Sir Tim Berners-Lee, who is the inventor of WWW. Okay, yeah, so it's a kind of knowledge representation based on there are lots of many experts from various parts of this world. They talk about, they defined layers of semantics. The bottom parts, the data layer, would be we use the RDF, which means Resource Description Framework. RDF is used to represent simple triples, and above the data layer is a schema layer. There are some simple vocabulary to describe the meaning of entities and the relations on the data layer. So the semantic schema layer is called RDFS, which is RDF schema. It's a basic hierarchy and vocabulary in it. So above, then the top parts, the top layer is the OWL, which means Web Ontology Language, which is an advanced logic and automatic reasoning. You can use the Web Ontology Language to represent the more complicated logic rules, but still on the development are rule language, semantic web rule language, SWRL, semantic web rule language, which is on the way you can use that rule language to represent the domain-specific rules to represent the knowledge of various domains. So we can conclude that RDF is the basic parts, the triples, and RDFS is the dictionary, and OR is the grammar and logical rule. Okay, so based on the 3 layers, we can use these two for your convenience to think about the 3 layers. Okay, yeah, the first that goes to the bottom layer is RDF, which is the Graph Data Model Foundation. RDF is the minimum data model. Its core is essential principle is everything is a resource. Everything is a resource, and the resource is identified by a URI, Uniform Resource Identifier. What is Uniform Resource Identifier? So, for example, you can see that when you surfing, when you access the wide web, you type in the URL on the top parts of your browser. That's the URL, Universal Resource Locator, which is used to locate the page you want to surf, you want to get. But we follow the URL, the syntax of URL, to be an identifier for resource because its uniqueness of URL. So, for example, when you type in a URL, then you'll get a page. Next time you type in the same URL, you get the same page as well. So we use its uniqueness of a URL to represent the resource. That's the meaning of a resource. So everything on the web is a resource, either a concrete or an abstract object. So everything is identified by URI. We can call it a URI. Now it has some IRI, a new form of URI is III. I is international resource identifier. I is still the same because IRI is used to encode all the typograph on Earth. Okay, so everything is identified by everything is a resource identified by URI. This ensures the global uniqueness and link data across the web. So you can have your resource identifier. For example, you have your URI on Facebook, on some other social website, or in your university. Your university offer you your personal web page that can be used as a URI to represent you. You are a resource on the web. Everything is a resource. Okay. For example, here is a URI, http://example.org/alice. Here's a URI, is an example URI. So the triples always say the statements, which is a subject. Subject is the resource being described. For example, Alice. Predicate are the relationship or the property. So, for example, has name. It says Alice has name, and the object is a resource or literal value. Literal value can be seen as a constant, some sort of constant. For example, here Alice is surrounded by double quotes, a pair of double quotes. Here it's a literal value. Its type is a string. So this triple, it says Alice, the resource Alice, the object Alice, the resource object Alice has name Alice string. Okay. So here is the basic idea of RDF. Here you can see this RDF example. This representation RDF can have many different many different syntax, maybe XML or JSON, JSON-LD, something like that. And here is we said is the turtle representation of RDF is I think is the simplest one, simplest representation of RDF. So here we have EX : Lisa. EX is the namespace defined here. It's defined as a prefix. So EX : Lisa is this URI followed by Lisa after this slash. So this we said this resource is a type. This property is defined by RDF. Is a vocabulary, is a word defined by RDF. If you want to know what type means, you can go to the RDF recommendation or the RDF standard document. You know what it means. But here we know as we say that Lisa is a type of dog. It's dog. This dog is defined in this namespace, in this space. Okay. Then the second statement is Lisa. Name is Lisa string. Here is a string. And then Lisa's owner is Alice. Alice is a object. Alice is a resource. Okay. Then this RDF example tells us Lisa is a resource type dog. Lisa's name is Lisa. Lisa is the owner, which is the resource Alice. Okay. Lisa, the dog Lisa has an owner. Owner, here we only know, you can say Alice is a resource, but we don't know what kind of resource is it. So based on RDF, it has the following limitations. RDF only stores the facts, and it doesn't know what a dog is. It doesn't know. You only know dog, but what dog is, or is that animal? Is a plant, or is a sheep? Is a table? No idea here. We only know that Lisa is a type of dog. And also, we don't know Alice must be a person based on this RDF example. So that's where RDFS comes in. We need more vocabulary to extend the RDF to make it more meaningful. So RDF schema, it's you can say this vocabulary definition language. The mission of RDFS is to aid some basic schema, some basic vocabulary, and some class hierarchy. So RDFS extend RDF to describe vocabulary semantics. We add some vocabulary semantics to make the RDF more meaningful. In RDFS, it defines classes and hierarchy. Use these words, class, RDFS. You can see here, RDFS define this word, class. It use this to define group of resource. For example, it's a class of person, is a class of animal, to make it more meaningful. So for example, animal is a type of class, and dog is a subclass of animal. So we can say dog, based on this extension, subclass, this class and subclass of, we can we know dog is a kind of animal. So within the RDFS, we can use the class to define the group of resources, and subclass of can be used to define the class hierarchy. And the inference power, if we know Lisa is a type of dog, and RDFS allows a reasoner to infer that Lisa is a type of animal. Okay, Lisa is a type of dog, and the dog is a subclass of animal. So we can conclude that, we can infer that Lisa is a type of animal. So more meaningful than, dog is something, but we don't know what it is. But by aiding this RDFS vocabulary, we know that dog is a kind of animal. And also we can have more vocabulary in RDFS. RDFS defines some properties and constraints. It used the domain, RDFS domain, to constrain the subject of a triple. Use this property must be an instance of this class, and range is used to constrain the object of a triple. So for example, owner, domain, dog, it constrains that the owner, when we use them, the owner relationship, the domain must be a dog. And for this statement, it says that when we use the owner relations, the object, the range must be a person. So these two statements says that the owner, the subject of the owner must be a dog, and the object of owner property must be a person, based on these two statements using RDFS vocabulary. So here is an inference example. If we see that Lisa is the owner of Alice, Lisa has owner of Alice, and we haven't explicitly defined Alice's type. If we don't define Alice, what Alice is, but based on this domain and range, the RDFS allow a reasoner to infer that Alice is a type of person. Alice, because Alice is the owner. Alice is the owner of the subject of the owner. So here Alice must be a type of person based on this statement. We can infer that the type of the class of the subject. Okay. Then the top layer is the OR, which provides richer semantics for deep reasoning. It's quite difficult. It's quite complicated, complex for this language, but it's very powerful. So web ontology language is the most expressive standard based on the description logic, which enables a powerful automated reasoning. The concept is based on ontology. Ontology is borrowed from the philosophy domain. Okay, but in computer science, we said that ontology is an explicit formal specification of a shared conceptualization. This simple sentence is used to very easy for a very simple definition for the ontology. Its full model of the domain is the most powerful knowledge representation of the domain, and OR's value is allow defining more complex relationships and constraints than RDFS. If we said RDFS is a simple vocabulary, simple set of vocabulary, we can use RDFS to define simple set of vocabulary. But if you want more complex relationship, you must use the OR. For example, if you are in the healthcare domain, maybe they need more complex relationships. So they need more powerful language to represent the relationships. So here is comes the OR, which provide more rich semantics for deep reasoning. And OR defines some property. The property defined in OR defines some that refines the definition of property. It divides the property into object property and data type property. The object property means the property related to resources nodes. Okay, so the object property, this property is used to relating to resources, and the data type property is a property relating a resource to a literal value. Okay. Traditionally, we used an oval shape to represent a resource, but we use a box to represent the literal value. But in this slides, I haven't given you any example of literal value in box. So okay, so for OR, it refines the definition of property into object and data type property, and there are some logical property characteristic. You can define some property as transitive property. It says that if A, P, B, and B, P, C, then A, P, C is transitive. For example, located is transitive. If Paris located in France and France located in Europe, then Paris located in Europe is an example for the transitive property. And for symmetric property and inverse property is defined as similar idea. APP, then BPA, it's a symmetric property. If we define property is a symmetric, for example, is symmetric. If Bob is sibling of Charlie, and then Charlie is a sibling of Bob, we don't. If we have these facts and we define its sibling of is a symmetric property, then we can deduce that Charlie is a sibling of Bob. And also inverse of defines the opposite relation. So for example, has author is the inverse of authored by. So if this facts exist, paper 1 has author Alice, and we define Alice as a inverse property, is the inverse property is authored by. So based on if this fact is true, then we can conclude that Alice is authored by paper 1. This fact exists as well. Or can define more logical constraint and reasoning. We can use the cardinality to refine the set, the new property without the name. For example, if it said that a PhD student must have explicit one supervisor, but how can we define this constraint? So we can set PhD students is a subclass. This class is a subclass of this class surrounded by the square brackets. Okay, the square brackets inside there has 4 properties says this is a type of restriction, and the restriction is on properties has supervisor, and the supervisors qualified the cardinalities 1, and the on class of researcher. This restriction is on researcher. So here is the subclass is used to define the subclass, define this property. It says the PhD student must have exactly 1 supervisor, but it's not really the true facts, because when I was a PhD student in Edinburgh, I have 2 supervisors. They gave me 2 supervisors. Of course, one is the principal supervisor, the other is the second supervisor. But yeah, so here is we use this to represent the constraint of this statement. And also OR used equivalence disjoint in equivalent class to define 2 classes have the same members. For example, car is equivalent to automobile, and disjoint with is used to represent an instance of one class cannot be an instance of another. For example, man is disjoint with woman. Here is an example of disjoint with. Okay, the power of reasoning, we can use this advanced logic constraint to make more advanced reasoning. Here is a summary of comparison of RDF, RDFS, and ORS for your reference. Okay. So why this matters? Why the 3 layers matters? The knowledge, because if we see from the knowledge graph application, first of all, this 3 layers as it can be used for data integration. We can use it for schema alignment, so for word, the vocabulary alignment. We use them over rules to map terms from different data sources. For example, recognizing that employee in one system is the same as worker in another. But for example, we can, in a system, we use employee to represent a class of something is hired by an organization or someone. And in another system, it's not used employee, but use worker. So we can use over rules to say that employee is equivalent to worker. So we can use this rule to connect. You can use this rule to align to different words, but we use the alignment, the rules to say that okay, these 2 sets are equivalent to each other. So that will be helpful for data integration. So then should be the automated reasoning. For example, if a patent's grant date is before its application date, an OR constraint can be used to an OR constraint is violated. We use OR to constrain the patent's grant date must after the application date. So that's kind of data quality check. For example, it can be used to infer or employee in the IT department's report to the CIO. The CIO, it's a new triple created, so we can make automated the knowledge discovery. So the search and the retrieval, we use them, or we can use them the layers to do more powerful search and retrievals. Things like graph RAG. RAG is retrieval augmented generation. Using this rich link context of an KG. KG can provide a rich context for large language model to reference to infer more accurate contextual answer. Okay, so that's I hear in this the topic of this slide said why this matters. It says the RDF, RDFS, and OR how can it be used for what? For knowledge graph applications. Okay, here is some three parts. One is data integration, automated reasoning, and then the search and retrieval. Okay, I think I used too much time on these two topics. Is up. So you need to take a rest. Stop temporary for 5 minutes, or
Okay.
This is
Yes.
up.
Yes. Okay, Prof.
Yeah.
Yeah.
Okay. So 5 minutes.
Yes.
Okay. Good.
Thank you.
So it's 8:07. So
Yes.
we'll be back on 8:12. Is okay?
Yes.
Okay. Yeah. So a break. 5 minutes
Okay.
break.
Thank you.
Okay.
Yes.
Okay. It's 8:12. So
Yes.
continue our lecture.
Okay.
Is that okay,
Yeah.
everybody?
Yes. Okay. Thank you.
Okay. Yeah. Based on our previous description, I think all of you have some basic idea of knowledge graph, and in the following parts, the third parts would be how to construct the knowledge graph. Okay, I'll turn off my. Okay, yeah. So it's okay. I'll go on.
Yes, please.
Okay, yeah. So now we'll talk about how to construct a knowledge graph. Yeah, here this part is more technical, So I will go through the slides more quickly because I think now we are behind the schedule. Okay. Yeah. The first would be the foundation would be the data ingestion, how to get the data and do some pre-processing. And the data source will be unstructured like text or PDFs or web pages. It requires natural language processing power. And also we have some source of semi-structured like a CSV, XML, JSON, REST API. It requires some parsers, some mappers. And also you can have some structured data. It's kind of relational database. So the data source can be classified into these three parts. Okay, for the unstructured parts is very difficult. So we need some more powerful technique like the natural language processing or some sort of large language model to do that, to process the text. And for the pre-processing step, either ETL or ELT, extract, transform, load, or extract, load, transform for KG. But yeah, there are two things. One is how to decleaning the data, and the second part will be normalization. The cleaning part is the duplication, handle missing value, format standardization. And then the normalization is to transform data into consistent canonical form. For example, how they will transform, will normalize the data formats, unit conversion, etc., which is kind of things similar to what so we say that data processing, most of the data processing, okay, or big data. A data mining process, okay, is kind of different. For data mining process, or data mining application, the most of the data sources are coming from semi-structured or structured. But here we have unstructured data, structured data sources. Okay. And the first step would be the define schema and ontology modeling. The schema, the role of the schema is to define the allowed entity, the nodes, the type of nodes, and relations. It's a blueprint for the graph. Is kind of to set up the structure, set up the framework of the knowledge graph construction. There are two dominant paradigm. One is property graph model. The other is RDF triple store model. In this talk, we focus on RDF triple store model, and the property graph model we haven't mentioned here, but it's similar to knowledge graph, but with more advanced property. We can have Neo4j, which is a commercial product used to do the property graph for the model. And for the triple model, is things like they focus on semantic web standard over RDFS and use formal logic. Examples Virtuoso. Virtuoso, I don't remember, it's from, I think it's a Germany company. And we used, in my lab, we used Virtuoso as the basis to store, as the RDF store for knowledge graph. And for domain knowledge, domain ontology construction, we need to define classes, define properties, define relationships, things like that. And we can use some famous ontology construction tools like Protege, offered by Stanford University. And you can get on protege.stanford.edu. You can get that tool. It's completely free. You can get some app version or a web version. It's quite good for ontology construction. And the second step is entity relations extraction it's most of this step is for unstructured data. Things like we need to recognize the name entity from text. Okay, the goal is to identify and classify name entity in unstructured text. Here is a very popular application of natural language processing, and also you can use large language model to do name entity recognition. It's quite good for that. Okay, so you can use rule-based gazetteers, regex. That's these two simple, the basic tools, or you can use the statistical machine learning and large language model. So in my lab, a student and me, we use a large language model to do name entity recognition. For example, here is a text from an unstructured text. Ada Lovelace worked at the Babbage Labs. So in this, we use the tool to extract entities in this text, and also classify the entity we extract. For example, this text we can produce Ada Lovelace is an instance of person, and Babbage Labs is an instance of org. Okay, so that's what name entity do. And the other thing is relation extraction. To extract relation within a text, we use the simple sentence. We use some example to illustrate the idea of relation extraction. So Ada Lovelace worked at Babbage Labs. So in this relation extraction, we extract words at relation from the text, works at the vocabulary, works at relation. So we're back to the goal of relation extraction is used to identify the semantic relation between two entities. So NER is used to extract entities, and RE, relation extraction, is used to extract relation between pair of entities. Okay, so these two technique is used for in this step. The third step is when you recognize the entity, then in the third step must do some sort of resolution and linking. The first is entity disambiguation. The problem is maybe the same text, same name has multiple meanings. So the goal of entity disambiguation is to determine which canonical entity entity A mentioned refers to. For example, we get a text apple is either a fruits or is a company. So we must do some this. We recognize apple, but we have to do some disambiguation, because in natural language ambiguity is quite is very. We used to see lots of ambiguities in natural language, so we have to do some. We need some technique to disambiguate the entities. Okay, then the entity linking coreference resolution. We must link entity, because the problem is the same real world entity may be referred to multiple, maybe mentioned for multiple times. Then the goal is to merge all the mentions into a single nodes in the graph. So for example, the CEO of Tesla, Elon Musk, is also the owner of X, the owner of X, the social website, the CEO of Tesla, Elon Musk, two mentions of the same entity. So these two mentions must link to the very same nodes for Elon Musk, say entity underscore E001. So these two mentions must link to the same entity. And the third, the C, is the technical. The technical approach may be rule-based or clustering. I will skip the technical detail here. So we skip to the step 4 is for knowledge fusion and storage. The fusion means integrate various knowledge graph. So the goal is to consolidate triples extracted from different sources to combine them. So the challenge is to, if we have some conflicting facts or different level of detail, for example, source A says the population is 1 million and source B says the population is 1.1 million. So which one is correct, or we need to combine to integrate to this triple and this triple from different sources, from source A, from source B, we must integrate to be one. That's the problem of knowledge fusion. That's still there is kind of a challenge here, and for graph database selection for our RDF triple store, we can select Virtuoso or some startup. It's quite new one, but Virtuoso is quite it's quite a famous one. It's quite good. Also, they have offered the open source, the free version. It's very ideal for semantic consistency and querying using Sparkle. So, for this talk, I will focus on suggest Virtuoso as the database, the graph database. Okay, so the data ingestion, we can use the specialized connector, for example, Neo4j importer or RDF loader for bulk loading. Okay, for Neo4j, this commercial product we skip here, but for our purpose, the RDF loader, we can use the Python version of RDF lib to load a whole for bulk loading of RDF triples. Yeah, then the fifth step is the knowledge reasoning and completion. We need the need for reasoning, infer new facts. Knowledge are often incomplete, so we can use the reasoning capability to fill the gap. There are two kinds. One kind of reasoning is rule-based reasoning. We use deduced. It's very classical one. We use deduced deductive rules. Said that if A and B and B and C, then A and C. We have seen this example before. And also a modern technique is we can use the knowledge graph embedding. But knowledge graph embedding is quite a new technique for solving the knowledge reasoning and the completion for knowledge graph. Okay, so we have this trans-E model, distinct model complex model, and this model is too complicated for the purpose of this talk, so I'll skip here. But if you are interested, I'll recommend you to study knowledge graph embedding. Just use the knowledge graph embedding to ask the ChatGPT, or use that to search in the Google search engine. You can get lots of stuff. You can study. The final steps would be the evaluation and quality assurance. The evaluation is the internal quality evaluation, which means intrinsic evaluation, and also we can have application performance, the outside, the external quality evaluation, extrinsic evaluation, and the evaluation. So we can review the low confidence triples, or we can filter is, and model retraining is triggered based on evaluation result. If the evaluation result is not good, so maybe we need to do some more things. Okay, so we can have an internal evaluation, external evaluation for this step. Summary would be the pipeline consists of the 6 steps. The big picture is knowledge graph construction is an iterative process, not a one-time deployment. So whenever you are in some step in the pipeline, you can, if you're not good, you can go back to the previous step. You can iterate on the loop on the same step for many times. Okay, and in the future trends, the increasing role of LLM, large language model, for zero-shot or few-shot extraction, especially for domain-specific knowledge graphs, and the synergy with graph RAG. So at the moment in my lab, we use the LLM for do the processing of unstructured text. It's very good, very easy, very good. The performance is quite good, and it's compared with classic natural language processing technique. Is good, and also it can be combined with the graph RAG, okay, to make the inference of LLM more concrete, more concise, more precise. Okay, so then we go to the first part. Fourth part which is application and use cases. Application 1 is to do semantic search and question answering. The problem of keyword search, formally, the search engine is we use some keywords to search. That's keywords. It doesn't mean the search engine understands the meaning or your intent, your purpose of the search. That's the traditional search. The problem is that, but now it is advanced to semantic search based on the knowledge graph solution. Okay, the mechanism is the queries are translated into graph traversal pattern. For example, in Sparkle or Cipher. In Sparkle, we can use the Sparkle language to do some graph traversal to collect things in the graph. But for the current parts, we can translate the queries into the queries, of course, is in natural language. We can translate the queries into graph pattern, traversal pattern, for example, based on the Sparkle. The benefits of semantic search is allow user to ask complex questions that require inferring relationship. For example, find all colleagues of the CEO who have also worked on project X, things like that. You can get the more needs, the more needs requiring inferring relationship. And also you can do question answering. KG can act as the source of truth. KG is a source of the truth. The NLP parses the question, map entities into KG nodes, and the graph query retrieve the factual answer. We can retrieve the knowledge graph to get the facts in the knowledge graph. But if you want to query the knowledge graph, you have to learn the query traversal pattern using some sort of query language like Sparkle. Things that it needs some technical background. It's not difficult for everybody. Okay, the second application, which the knowledge graph can be used for machine learning, feature engineering. So it can be used to model performance. The KG can provide the structured features and relationship contexts that are often missing in plain feature vectors. The feature vector is something like an embedding vector we use to represent a word or something in the text to represent the meaning. But for embedding vector, it's only a vector. Then it lacks of the structure, feature, and relation context, things like in knowledge graph. So we can extend the knowledge graph to be graph embedding for features. And the second, you use the graph neural network, GNN, for that purpose. GNN is a model like graph convolutional neural network. In the computer vision, there's a famous neural network model called CNN, convolutional neural network. And also we can use the convolution to extract the convolution mechanism to extract features in natural language text. Okay, yeah, but it's too technical. I'll skip it here. The third application would be enhanced recommender system. For traditional recommendation, for example, we use the collaborative filtering. It's not good for cold start problem. For example, for new user and new items, when you enter to the recommendation system, there are no reference. It's like expandability. Why? It's when a new user enters, it's a cold start problem. It doesn't have any relationship with the existing things in the recommendation system. So it's a problem. And also the traditional recommendation system lack of expandability. For example, why was this recommended for someone? And when we use the knowledge graph solution, we use the path-based recommendation. For cold start problem, we use the items property. We can use the items type, brand, category already connected in the knowledge graph to link to the existing users. So just solve the cold start problem. And the mechanism recommendation system are based on connecting a user node to an item node via meaningful path. For example, user link category to items. Expandability problem, the path itself provides the reason for recommendation. An example is recommend movie B because user watched actor X and actor X star in movie B. So that's why I recommend movie B for this user. And this is the path in the knowledge graph. So we use the path to provide the reason why for the recommendation. It's the expandability. So the fourth application is data integration for enterprise silo problem. The enterprise silo problem, customer, product, inventory, and sensor data reside in separate, often incompatible databases. So we can use the knowledge graph as the solution to centralize the semantic layer. Here, KG acts as a unifying layer, a federated hub. It's a hub that connects schema from disparate source system. The benefit is enable a true 360-degree view of a complex entity. For example, it connects a customer nodes to their purchase history from ERP and support the tickets from CRM and website activity from logs. They're all from different data sources. Conventionally, it was because of the silo problem, these sets are separated, but now we can use the knowledge graph as the unifying layer to unify these different sources. And also you can provide the data governance. The KG schema can enforce shared meaning and data lineage across the organization. When we deep dive the KG plus knowledge, the large language model, which is the technique of graph RAG. Now it's quite good. If you want to do the research, here is quite a good idea. And for the LLM, the large language model is limited because it is a local. It can very easy to prone to hallucination, and the large language model, after its training, it lacks the up-to-date and domain-specific factual knowledge. So we can use the knowledge graph knowledge graph, and in the RAG, retrieval augmented generation, we use KG as a structured factual memory bank for the LLM. The process is, when you user ask question, system retrieve the relevant facts from the KG, then the LLM is given with the retrieved facts as context to generate accurate, grounded answer. That's the use of the LG. As far as I know, the quite famous company about RAG is called Langchain. They provide some KG in their RAG mechanism as well. So the result would be more, the answer will be factual, explainable, that's drawn from the latest, the up-to-date enterprise data. It can be used for prompting. The structure of the KG itself can be used to engineer more effective prompt for LLM. Because some user question through knowledge KG retrieval, you get the context. The context combined with the questions sent to LLM to get more factual answer. Okay. So here we can have a last example. Last use case is the financial crime detection. The challenge is financial fraud and money laundering relies on complex, non-obvious relationships. It's separated in quite different sources. And based on the knowledge graph modeling, or notes things like accounts, transaction, people, location, IP addresses, etc., etc. And age is used to represent transfer to, share address connected via IP owned by something. Okay, so the KB power detection would be that we use the graph algorithm, for example, PageRank or community detection, and traversal query identify suspicious patterns. For example, the pattern, an example pattern is that identify a closed loop of transfer where the funds return to the source account via a chain of intermediate unrelated individual. So use this closed loop maybe is suspicious, the kind of money laundering. We can use that for financial crime detection. Okay, of course, it's not simple. As we need some more technical work. Use case example: pharma R&D and drug repurposing. We can use knowledge graph in pharma R&D and use KG to do some repurposing of a drug. The challenge is massive volume of scientific literature, and the key connection between entities are buried across papers. There are lots of papers, but things inside the papers, it cannot be processed automatically by machine. That's the challenge. So we can use the model KG modeling. We extract the gene, the proteins, the diseases, the drugs, symptom, clinical trials as the node of KG. And also we do some sort of relation extraction from the papers about the treat, interact with, causes, exhibits, symptom. We can use the KG to model this in pharma R&D and drug repurposing. Okay, for drug repurposing, the mechanism is we use knowledge graph KGE, knowledge graph reasoning to predict potential links between an existing drug and a new disease, to connect existing drug with new disease. Of course, the connecting the links must be safe and FDA approved based on their shared connection to gene or proteins. Of course, I'm not expert about what is genes and proteins, but for the expert for pharma R&D stuff, they know the idea. So KG knowledge graph, the technical knowledge graph is widely used in pharmaceutical industry. So for example, we can predict that the drug X could treat disease Y because both are linked to the same protein. Okay, things like that. But I think this use case must be more complicated than what the slide showed to you. But I think it's a very good, it's a good use case for knowledge graph. So the summary, the final thoughts is the power of context. Knowledge graph can provide powerful context. So the knowledge graph transcends simple data storage. It's more powerful than simple data storage. It's above the simple data storage. KG encodes the meaning and the structure of knowledge. And KG are foundational layer for next generation of explainable AI and the grounded LLM. So when the knowledge graph is not a new stuff, it starts actually from the early 21st century. Okay, so but now we can see after 20 more years, we can see that when we can use the knowledge graph as the base for the next generation of explainable AI. So, for example, if AI is expert, but for an expert, it must have the capability of explanation for what, why, how it gets the result. Okay, and also the knowledge graph can be used as the ground for LLMs. And the key takeaways, whether the financial insight, scientific discovery, or better search, the KG can be used as the unifying fabric that connects enterprise knowledge. Okay, that goes to the we still have how many slides? Maybe how many slides? Okay, we still have 4 slides. Yeah, we are going to finish this talk. So yeah. So the fifth part will be the tools and future challenge. In the KG ecosystems, there are some the fundamental tools. The first is the graph database we use to store triples and for querying triples in the store. Here, I would recommend use the Virtuoso or here's Apache. Gina is a kind of framework that I'm sure it's good. I heard about that, but I'm not sure whether it's good or not. But I would recommend to use we can use the Virtuoso graph database. And for extraction and construction framework, we use Stanford Core NLP for NER or NRE, name entity recognition, and or relation extraction, which are two fundamental tasks, fundamental work for extracting things, entities, and relations from unstructured text. Also, we can use open information extraction system, but I would highly recommend use the use the LLM pipeline to do the process of unstructured data. Okay, the tool, because that's very good. In my lab, we use that tool, the LLM, frequently. So finally, is the visualization and exploration. It is essential for debugging, validation, and user-facing application. For example, things like that. I haven't used that visualization and exploration tools. For KG maintenance challenge, because some knowledge is dynamic, its temporal evaluation is so evolved through time. So the real world change, and so the KG must reflect the change. The solution is use the temporal graph model that's version facts with timestamp, automated incremental extraction and refusion pipelines. That's quite a very big challenge, because the knowledge is dynamic. We have to keep the knowledge graph as up to date. So we need some sort of, we have to take care about this. And the scalability and performance, the problem is the number of nodes, and age grows. The graph traverse complexity improves rapidly to be big data scale. So the solution may be we can use this graph processing, share the graph database across cluster, and optimize indexing. That's more technical. And for the data quality and trust, the problem is the propagating error from source data or extracting inaccuracy. For example, if you extract the entity which are not accurate, so it will propagate the error through the knowledge graph path that will cause the problem. So how to make your data to be good quality and trustable? The solution may be we can integrate confidence score on every triple, running this consistent check after ingestion, and implementing a human in the loop validation process. So I think human must enter the loop for the validation process. That's quite a challenging problem. Okay, and the research frontiers, the key challenge is we need some sort of automated schema induction and better integration of unstructured data and explainable, trustworthy AI. That's the future that's still a research problem. Okay, now we goes to the conclusion and Q&A. The conclusion is the KG, we used a unifying vision to see the knowledge graph. So knowledge graph can be as the semantic foundation for that integrate data, power, smart application, and ground the modern AI system, especially for large language model. And in the journey, we move from the definition of triple through the rigorous construction pipeline to powerful application, and finally we go to the maintenance and research challenges. And for your next step, if you are interested, if you want to do some sort of knowledge graph work as your next step, so I would suggest you start from simple. For example, you can do some sort of domain-specific knowledge graph. Maybe you can get the text from your university website, for example, the regulation rules text, and use that to convert that text into into a knowledge graph. So of course you have prepared I'm not sure on your university website, the language is based on Indonesian, right? So you need some sort of Indonesian natural language processing capability, or some sort of large language model is able to process Indonesian. Okay, so that's the happy ending. Will be a short question and answering session for this talk.
Thank you very much, Professor Ye, for your inspiring presentation.
Yeah.
Now we move to question answer session. Is there any question? Please raise your hand or type in at the chat box, please. Yes. Mr. Surya, please.
It is very wonderful and very inspiring, of course, and a lot of questions.
Okay. Sure.
And this is very relevant to Indonesia, as you know that we have more than 700 languages, I think.
700 languages in Indonesia?
Yes,
700,
yes.
are you sure? Oh, no.
Yeah, you can search in Google and how many language in Indonesia, and there are a lot. 700 languages. Actually, Papua has around 300, and I think this is become the potential for research. But if I hear from your technical step,
how many official languages in Indonesia? How many official
more
languages?
than 700. The official is Indonesian language.
It's one. It's only one.
One language. Yes.
Okay, that's okay.
Yeah.
It's quite different from Indian language. As far as I know, there are more than one official language in
Yeah.
India.
Sometimes
So
we use
one,
Japanese.
that's lucky.
Yeah, Japanese language is also available at some islands, but not for all. The question is that. So because we have so many languages, we have to start somehow in a simple way to have a very realistic roadmap for research for the student. For example, there are so many hobbies. For example, start with notes from local traditional songs. For example, there are a lot of traditional songs with their own language, and it is possible to have a little bit complete steps from the digitized step, normalizations, and then what literacy, reliterations, and then go to RDF. So what is your experience to make a realistic roadmap for your students? Because the problem is so big, so wide. Okay, that's the questions.
Yeah.
How to make the life is simple.
The life is not so simple.
Yeah.
Well, knowledge graph, the life is not so simple. I must say. So at the moment, I used the regulation rule text on our university website. I have collected the text is about 571 files, and all are in HTML formats. So I have to extract the text from the HTML files. And that's okay. We can use the beautiful soap. You use the beautiful soap model to do that extraction task. Then we can. I have the pure text. I have to divide the text into revision fixed history and the main parts of the regulation rules. So, but based on that, so I can the next step I will use the large language model. For example, things like GPT or some Llama or something to help me to extract the entities. I mean, the entities are in Chinese, in Mandarin, in Chinese characters. So it's quite a challenge for the large language model to extract the Chinese stuff, the Chinese text, the entities Chinese text. I think that should be the same thing your case. But I think that luckily, because the population in this world, the use of Chinese is more than Indonesia is. Am I right? I think that's right. So there's still we can have some Chinese large language model inference capabilities for us to do that sort of task. Yeah. So that's I think I must say that's really a challenge to do that. Okay. But I think just for study purpose, I think you can start from English text. Okay, some simple English text that you can start from. For example, some web pages which is written in English, so you can take the web page in HTML and then extract the text from that. Then you enter the KG construction pipeline step by step to get the knowledge graph. So you can learn that. After that, you can when you learn the knowledge graph construction pipeline, then I think you can start the Indonesian language as the next step. I'm not sure whether I answer your question or not.
Yeah, of course. For Indonesian language, we have an example, for example, using Indo-BERT. So it is developed by Universitas Indonesia and also some university there. Mm-hmm. And it is used, for example, Sahabat AI. It is in Indonesian language. So if we start from the local language that is not digitized yet, it is very hard, of course.
Oh yeah. I think that's the I think it's still a challenge problem, right?
Yeah. Okay, thank you.
So welcome. Any question?
Okay.
Hello, sir.
Hey, yeah,
Yes,
hi.
please,
Hi.
Pak Daniel, please.
Thank you so much.
Daniel,
Eliazar.
Daniel. Hi, Daniel.
Yeah. Is my voice audible?
Yes, of course.
Okay.
Yeah.
Thank you so much. So actually, I have to appreciate these sessions because I find this topic is so interesting,
right?
And I got some insights regarding my studies. So now I'm also continuing what's asked by Sir Surya. Actually, I am actually doing also research in indigenous language in Indonesia.
What
so as you know, indigenous language. It's just like local language
processing.
Yeah, right? Yeah.
So it's NLP or large language
NLP.
model?
It's an NLP.
So what kind of which tool you use? You use Spacey or?
Actually, now I'm working on, as you know, on your presentations, I note some important terms like LLM, but as we know, LLM has limitations when dealing with low resource data.
Right. Yeah.
Right, sir? Yeah. So that's the challenge in indigenous language. As we are facing a limited amount of data, we have to. So my research actually focusing on how we create an embedding that can still enrich in meaning and context, but still, but also can be harvested from the low resource data. So my questions is, taking on all the inspirations from the cases you are given to us, can we utilize some traditional methods of to replace all that mentioned LLM? So yeah, because from what I can listen from your presentations, you really emphasize the importance of LLM. But in our field of study, it's hard to depend on LLM. So is it still possibility, sir?
Yeah, because modern techniques like LLM and NLP technique, they're based on training on large data sets. So that's the problem. Okay, and most of the data sets, I think more than 95 or 97% of the the data set used by the large language model, things like OpenAI's GPT, something like that. And even for Mandarin, for Chinese, it's occupied only a very small part. And also in Taiwan, we have a dialect of Chinese. It's called Taiwanese. It's almost no data set mentioned in that. So we are struggling, try to do this. So we collect the data set for Taiwanese, data set for the local Taiwanese. So we want to use it to train a small language model. Things like maybe some less than 1B, the small language model. So that is easier. So we can to train model is that the basis we can use that to train to infer Taiwanese text. Things like if you can collect, first of all, you can establish the data set for Indonesian, your official language. You can start from doing the data sets, your vocabulary, your sentences, and so you can use that as the basis to do some more advanced knowledge graph construction. So first thing is, but you mentioned that is there any is there any traditional
non-LLM, yeah, like
LLM?
traditional.
Well, I would say if you don't want to use LLM, I cannot see any traditional technique. I mean, the algorithm mentioned in the NLP textbook, I cannot see the possibility to establish the application, the work of Indonesia. As I think it's not good idea to use traditional algorithm. So I think it's better for you to train your small language model. Starts from a small language model, but the important thing, the fundamental thing is yourself to create your own data sets. That's maybe I would say that would be the code as a sovereign AI. The terms are mentioned by Jason Huang, who is the CEO of NVIDIA.com. All right, so that's maybe an idea, but still is a challenge problem. Even for me in Taiwan, we struggle for Taiwanese. We want to do, and we have a colleague who has established the Taiwanese data set for the training of large language model. I'll say the small language model. We're not trying to challenge the big company, the big LLM like OpenAI or clouds or something. We just want to do that small language model for our own purpose. So maybe it's the same idea for Indonesian language processing. Yeah.
Okay, thank you, sir. So maybe some methods like transfer learning has a potential to do, yeah? Like we are training.
Maybe it's based on statistics, but still statistical methods. You need some. It's better to collect more data, right?
Okay.
Yeah. So we can resort the problem to be the problem of data collection, the data set. Yeah.
Sure, sir. And the last question, sir.
Yeah.
If I can ask you to recommend us, like, what's your favorite resource to study about knowledge graph that you think easy to understand, but also like details in information? Thank you, sir. If you could.
You mean the resource of for the study of knowledge graph, is that?
Yes, sir.
Yeah, I
maybe like a website
recommend okay, maybe the problem of my network. It's okay. I will switch to another network.
We can still hear you, sir.
Okay. 1 minute. Okay. Okay, and then open modify, so we can change the we make things easier. Okay, so you mean the resource for learning knowledge graph? As I would recommend the resource, I'll type here. I will leave. Hold on. Knowledge graph professor. Okay. Yeah, I have left a web page on in the message. You can try to see the knowledge graph lecture offered by Professor Halasak. Okay,
Thank you, sir.
Yeah, no problem. It's very good idea. It's very good, and also it's the best thing is it's completely free. And it's very high quality lecture. I would recommend you to go through the lecture, the 6-week lecture. That will make you stronger on knowledge graph, I think. Yeah. Okay.
Thank you so much, sir. Thank you. God bless.
Thank you. Because we are running out of time. Last question, maybe? Pak Martin or else? Do you have any question?
Yeah. Thank you, Baba Bang, and thank you, Prof. Ching-Long. That's very interesting.
You're Martin Satu.
Yes.
Okay.
Yes, Martin Satu. Wow. So I'm also interested in NLP like Daniel. So now I'm interesting to help the indigenous children for the very basic in literacy and numeracy. So my question is, do you have any like a studies or even it's a project that demonstrating maybe like I say effective implementation of KG in literacy or in the education sectors for the indigenous? So because like Daniel said, this very low resources languages and also some of the digitalized resources is very limited. So I think it's a good in the education sector. Maybe you have like a recommendation, also your experience to like apply to the area in the Indonesia. There are many indigenous people that not to many challenges in the access to education for the basic one. Yeah, that's my question, Prof. Thank you so much.
Okay, I will recite your questions. You are interested in NLP, and you want me to give you some recommendation about how to work in Indonesian NLPs. Am I right?
Yeah.
Or okay. So are you? What is the background of your NLP techniques, your theory about NLP?
It's about embedding to like classification of the text, but now I'm using the Bible text because some of part of Indonesia have the language or written language in the Bible. So the very simple one that how to using LSTM or BLSTM with embedding word.
LSTM, something.
Yeah, to identify the simple one like a New Testament and Old Testament and so on. That's it.
So can I ask a question? Is do you have a good data set for Indonesia?
Like a Prof. Surya said, we have some data set that I think is quite right now. It's quite helpful. I mean, what I say, it is maybe I say it is good right now, but to translate to another language, a mother language, that's the very limited one.
So
but
maybe
if
you want to apply the NLP to construct knowledge graph, maybe I recommend you to do some training using some training, maybe use the fine tuning for some LLM. Use your Indonesian data sets, for example, for the purpose of name entity recognition. Maybe you can prepare the data set for name entity recognition in Indonesian. So maybe you can use that data set as the basis for the fine tuning. It's based on some large language model or some small language model, not too big, so that you can get your fine tuning results. So maybe it can be used for name entity recognition. So after name entity recognition, so maybe you can do some relation extraction. Yeah, so that will connect it to a knowledge graph construction, maybe. Yeah, so if you have some basic data set in Indonesia, maybe you can prepare for the data set for fine tuning, for some specific task of fine tuning, things like NER, name entity recognition. I would recommend it to do that, maybe. So that will be on Indonesia. Maybe it will be the first one, the first name entity recognition in Indonesia in this world. Maybe, I don't know.
Yeah.
Yeah.
Okay. Thank you, Prof.
No problem. Yeah.
Okay. I think that's the last question, Prof. Yeah.
Okay.
Okay. Once again, thank you very much for your sharing valuable knowledge for us.
Okay.
We really truly appreciate your time and contribution for us. Thank you for all guys and students for participation and attendance. And now I hand over the session to Mr. Surya.
Okay.
Thank you.
Yeah, Professor Dr. Surya, I will discuss with you about your visiting next year.
Oh, yes, thank you.
Through email, or if you use the line, we can interact with each other. Okay. Yes. I find some very good IoT. I think you're expert in IoT, right? Or
yeah, I play with IoT too.
Come here to do some IoT AI plus IoT on
yes.
Fishing and farming, things like that.
Yeah.
I'll talk to you later on in the email. All right.
Okay. Thank you.
Yeah.
So thank you very much, Prof. For your wonderful and inspiring lecture about knowledge graphs. It was really interesting, and I believe many of our students are now excited to learn more about this topic, of course. We hope that this will be the beginning of our collaborations, maybe some mini research projects together in this near future, especially with the local language, in the indigenous language. So let's keep the spirit of collaborations alive and growing.
Yeah.
And once again, thank you very much.
Yeah,
Prof.
and of course, all of the audience of this talk, if you are interested in NLP, LLM, and KG, things like that, you can communicate with me through email, or you can get my email from Surya Professor. Right?
Please,
Okay.
big applause to Professor. Yeah.
Yeah.
And before we close, we would like to have a group photo together with Professor. Yeah. So I kindly ask everyone to please turn on your camera for a moment so we can take a screenshot of a memory of today. Wonderful guest. Okay. Let's smile. Thank you. Please open your camera, please. We are waiting for the camera.
Whoa.
So many students here. Only 50% has camera. Hey, come on. Please open the camera. Okay. I take a screenshot. 1, 2, 3. Okay. Thank you very much.
Thank you. Thank you.
Thank you,
very much.
Prof.
Good night.
Thank you. Good night.
Good night.
Good night. Bye-bye.
Bye-bye.
Bye.
Bye.
Thank you.
Terima kasih Pak Surya.
Terima kasih.
Terima kasih.
Terima kasih.
Terima kasih.
Selamat. Saya tutup ya.